In this lesson, we plan to find the arc length of something that's called a smooth curve. This is our first truly BC only topic. A smooth curve is exactly what you think it might be. There's no kinks in it. There's no, sharp turns. By definition, it means that the derivative is also continuous. Let's start by taking a look at this very simple warm-up question. Find the length of segment AB. I've got a segment that is graphed on the coordinate plane, and we know that we can't just count diagonally from A to B. We have to basically use the distance formula on this. Hey, where does the distance formula come from? It comes from the Pythagorean theorems. I could actually take that segment, I could turn it into a right triangle by extending a segment straight down from B, and then come across over here to B, and then I've got R to A, and then I have myself a right triangle, and then I could just use the Pythagorean theorem. Again, exactly where the distance formula comes from. All right then, so let's get our change in x down here. So that's a 5, that's a -2. That gives us our delta x is basically equal to what, 7? Okay, and then coming over here for the y coordinates, that's a 6. That one's a 2. Our delta y is basically equal to what, 4, right? 6 minus 2 gives us a 4. Okay, all right then. So the distance between A and B should be equal to the square root of the change in x squared, so 7 squared, plus our change in y squared, 4 to the 4th. What? Are you even kidding me? All right, there you go. You can save stop that if you want to, or come on. We can work this out. This is a 49 plus 16. That would be 50 plus 15 more is the square root of 65. There you go. All right, and you can see very clearly in here that this is an a squared plus a b squared. We took the square root of that whole thing. All right, that has something to do with our goal for this particular lesson, which is all about finding the arc length, finding the length of some sort of curve that is graphed in the coordinate plane. Could be a function, doesn't have to be a function. Could be some implicitly defined equation. Okay, do you know what this thing is? Of course you know what this thing is. You've played Minecraft. You've been alive for the last 10 years or so. Okay, so we've seen this series of pictures before. We talked about Archimedes' method. If you've been in this honors geometry program a couple of years ago, you probably even approximated pi by using Archimedes' method. And in this method, Archimedes approximated basically the circumference of a curve, in this case a circle, by using polygons with straight sides. We're going to do something similar in order to find the arc length of some kind of curve. So speaking of curve, here we've got one, some strange curve here. So imagine it, if you will, that you position one person right here and you position another person right there. And the arc length, of course, would just be, hey, how long does it take you? Not how long, but how far would you have to travel to get from one of those persons to the other person? Or let's say that this guy's really strong, beep, 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 and this guy is also really strong. I'm saying guys, but they could be, whatever gender you want them to be. And one walks this way, one walks this way, and they straighten this whole thing out. And you measure the length of that. That, of course, is the arc length. Okay, so it's really hard to measure a curve, but it's really easy to measure a straight line. So that's what we're going to do, is we're going to break this up into a series of straight line segments. How does that help us? Well, just like from the warm-up activity, we could just turn this thing into a little right triangle right there. Use a little Pythagorean theorem on it, and we can just add up all of those little segments. We can get closer and closer to the actual length of that curve if we just increase the number of little line segments that we have here. We've got 1, we've got 2, we've got 3, we've got 4, right? We can go all the way up to, I don't know, maybe an infinite number of those things. Okay, so let's start by looking at just a random little line segment on the ith subinterval. It'd be sort of like this. So I'm going to take this little portion of the curve. So let's say that I partition, come on, laser pointer, I partition my interval And this is just going to be one of those little intervals. Same kind of thing that we did with the area, but now we're just going to do it with lengths, little line segments. Okay, so if I wanted to find the length of this little segment, of course I need to use the distance formula, which needs a little right triangle in it. So let's throw our little right triangle in it, just like we did in the warm-up activity. And we need our two lengths. So down here we have a delta x, here we have a delta y. It just has little subscripts of i's in it because it's in the ith sub-interval. And so now if I want to find the distance between these 2 points, which is the length of the segment, I'm just going to employ the distance formula, otherwise known as the Pythagorean theorem, thusly that the length of this ith segment should be the square root of delta x sub I squared plus delta y sub I squared. Okay, so there's the length of one of them. Let's go ahead and sum up n of them for the whole entire interval. Okay, so we have a summation from I equals 1 of the square root of, we have that little distance formula. Hey, isn't that a Riemann sum? No, this is not quite a Riemann sum. Just take a look at it for a second. There is something crucial missing from it. We have some sort of function inside here, sure, but we're missing a width. Not only that, this has y's in it and x's. That's kind of a problem. Okay, so we're going to try to fix this. We're going to try to turn it into a Riemann sum because, the limit of a Riemann sum is a definite integral, which, is pretty easy to solve as we've come to discover. All right, so how can I get this to be a Riemann sum? We just said that we're missing the width, so let's multiply this by a fancy 1 so we can get a width in here. Great, so here's our fancy 1. And again, I chose this one specifically so that we can get a width, this delta x sub I here. The extra delta x sub I down here in the bottom, we're just going to pair it up with this square root, and it'll just become part of our function. So it'll look sort of like this. Boop. Okay, so far, so good. So it's almost there. We're just going to clean it up a little bit. We got to get rid of this delta y sub I inside here. The way that I'm going to do that is I'm going to take this delta x sub I, get it into the square root. How do I get it into the square root? Well, I am going to square it and then take the square root. Now, of course, that neuters it. That makes it positive, but delta x sub I should be positive anyway, so it's a-okay. All right, so now we are ready to cram this delta x sub I into the square root that's on the bottom, and this is what it's going to look like. I have, of course, delta x sub I squared divided by delta x sub I squared. That's just going to be 1, and then we'll pair this up as a single fraction, and now we have ourselves a Riemann sum. We can take the limit of that Riemann sum. How do I know this is a Riemann sum, first of all? Well, we have a function now, and then I have my width over here. And I know what you're saying. I know what you're thinking. This has a little y in it, but we're going to fix that in just a second here whenever we take the limit of this Riemann sum, okay, which is what is about to happen here. We're going to take the limit as n approaches infinity. By definition, that is a definite integral from a to b of, we got to think about this for just a second. So if I take the limit as n approaches infinity, what is going to happen to this term here, right? We have kind of an issue that it has a little y up in it. Well, this is approximating this, no, it's not approximating, this is actually the slope of the secant line. So as n approaches infinity, that's the number of subintervals in our partition increases. Remember that, okay, so it's like this, that the width is going to get closer and closer to 0. So let me take it back a minute. If I take the limit as delta x approaches 0 of, this is the slope of a secant line, delta y over delta x, you get the slope of the tangent line, right? That's basically the definition there. Okay, now, of course, this is not exactly what we have right here, but they are equivalent to each other, because as the number of partitions increases without bound, then of course our width goes to 0. All of that to say that as the limit as n approaches infinity, this thing is just going to turn into our derivative dy dx. So here is our arc length definite integral. We got the length is equal to the definite integral from a to b, square root of 1 plus This is basically the derivative of our function squared with respect to x. So we can leave it in this Leibniz notation that we have right here, or we can put it in the, the little prime notation. All right, so here we go. Definition of arc length. Let the function given by y equals f of x represent a smooth curve on the interval from a to b. So smooth curve, it'll be on here on the screen in just a minute, just basically means that your derivative is continuous. The arc length s of f between a and b is this definite integral that we just derived. So s is equal to the definite integral from a to b of the square root of 1 plus the derivative squared with respect to x. Okay, so remember that this came from basically little distance formula, so that should help you remember that there should be it's almost like an a squared plus a b squared that's right here. It's just that your b squared is just going to be your function squared. And then just one last little bit, talking about a smooth curve just simply means that the derivative is continuous on your interval.